Okay, so far we haven't talked about the singularities of holomorphic functions, okay? But singularities play a very important role. So holomorphic functions can be thought of as two-dimensional versions of solutions of, say, Laplace's equation. So in some sense, a two-dimensional electrostatic field. And there, the role of charges are played by singularities. Okay, so there's a beautiful analogy there. So what I'll do is that I'll also make available my lecture notes from PSI from many years ago, where I gave a set of 4 lectures as a refresher course for complex analysis. It'll give you an overview of complex analysis. It won't make you an expert, but if you have done complex analysis, you want to review some of the concepts, it'll give you an overview. Okay, so next topic is the singularities of a holomorphic function. So for example, if I take f of z to be, say, 1 over z minus a, then it should be obvious that z equals to a is a singular point, right? For f of z. Right? This is a. What about f of z is, say, 1 over z minus a whole squared? This is also a singularity, right? You guys agree, right?
Yeah.
Yes, sir.
Yeah.
Okay, now let's look at some other kind of singularities that say what about e to the power z? Does this have any singularity on the finite part of the complex plane?
No, sir.
No, right. What about this guy? I'm going to stop writing f of z for everything. What about this guy? Sine of z, this guy?
No, sir.
Okay. What about sine of z divided by z?
Yeah, this one would have a z equals 0.
It has a removable singularity at z equals to 0. Okay.
But it is, yeah, I mean, it's not a singularity, right? Because for small values of z, this is z by z. Right? So, so yeah, these are not, so we have seen some singularities. Let's look at another singularity, e to the power minus 1 over z. Does it have any singularity?
At z equals to 0.
Right. And okay, so these are singularities. There are 2 types of singularities. One is like the poles. Poles are these things. Okay. And poles are usually go away if you multiply by some appropriate function, right? So for example, from here, if I multiply this by z minus a, then the resulting function will not have any poles. Similarly for here. But this guy, if I expand this, you see that 1 minus 1 over z plus, say, 1 over 2 factorial z squared, blah, blah. There is no finite power of z that we can multiply to get rid of the singularity, right? So those type of singularities are called essential singularities, I think.
We can multiply e to the power plus 1 by z.
Yeah, but that's not a, that's not allowed, because that's, you're multiplying it by an infinite power of z, right? Okay, so now suppose that we have a holomorphic function f of z. It's holomorphic, but has singularity, has a singularity at, say, z equals to z naught. Then you can show that, f of z admits a power series expansion around z equals to z naught in an annular region. Okay, so sorry, that is not the most elegant way of expressing what I want to say. But what I want to say is this. Suppose you have a singularity at z equal to z0, and suppose this function also has a singularity at z equals to z1. Then these 2 points, they create an annular region, right? So sorry, it's let me just draw this other z close by. So suppose that this is a z1. So these 2 points, singular points, they create an annular region for this function. Okay, and so if z naught is a singular point, that in this annular region, f of z admits a power series expansion, and the form of the power series expansion is going to be given by, their terms. I'm not going to write all the terms. It can be infinite or it can be finite, depending on the function. But, it'll have terms like these. And okay, so this series expansion, the series expansion is called the Loha series expansion. Okay, so this expansion is only valid between z naught and the next singularity. Okay, in an annular region bounded by z naught and the next singularity. If the function has only one singularity, say at z naught, then it's valid over all of the complex plane except at z naught. Okay. Okay. So these coefficients are, so these are the coefficients. Okay. So of course, it's these terms, the negative power ones, which blow up as z goes to z naught, right? These terms go to 0, and this doesn't change. Okay? So these coefficients of...
Sir, I didn't get the point of 2 poles and a region in between.
Yeah, all I'm saying is that this is a theorem, and I'm not going to prove it, is that if you have a holomorphic function, so it's holomorphic in some region, so on this plane, but it has a singular point at z naught, and then you can find an expansion of this function around z naught, which has this form.
So the second point is not included in the expansion.
If there is another point, then this expansion is valid between this point and this point.
Okay, got it.
Okay. So, right. Okay. So the coefficient, of course, the thing is that now, you can expand this point around Z1 as well, this function. And then you'll have an annular region which is centered around Z1 and whose radius is bounded by Z0, right? So it'll be like this. And that series expansion, the coefficients A minus 2, A1, A0, A1, those coefficients will be different. Okay? So this is a series representation around a certain point. So the idea is that, sorry. So it's a bit like, it's a bit like, the coefficients as you know, if you take take a function and do the Taylor expansion around some point, the coefficients of the expansion will change depending on which point you're expanding it around, right? So the Loha expansion is essentially a expansion for singular. It's kind of a Taylor series expansion, but for singular points, around singular points. It's not a Taylor series, of course, because Taylor series is not singular.
Okay, got it.
The Taylor series never has negative powers of the expansion parameter, right? Okay, so now comes the very important statement. The coefficient A minus 1, that is, this guy, has a special status. This is called the residue of the function f of z at z equals to z0, okay? So this is the definition of residue.